Hello, everyone. It's 3:30. Let's get started. Very happy to welcome Jessica Stryker from North Dakota State University, who works in algebraic combinatorics and physics and dynamics and all sorts of interesting things. Her website had a very high concentration of words I've never even seen before, so I'm very excited to learn some of those in this talk.
All right, yeah, thanks so much. Thanks to everybody for coming. I'm really pleased to get to visit here at Waterloo, the home of my longtime collaborator, Oliver Pachenik. And so this work that I'm going to tell you about it does have a lot of words that you probably haven't seen put together before, but it's joint with Christian Gates, Oliver Pachenik, Stefan Fannerer, who's over there, and Josh Swanson, who's in the back. You can identify many of us by these cool t-shirts that Stefan made for us, which have our main new combinatorial object, an hourglass plabic graph on it. So I hope by the end of this talk, you'll understand a little bit more about what's on our t-shirts. So here's kind of the overview of my research. So where I started out back in my PhD, I liked learning about these matrices over on the left, alternating sign matrices. And then after exploring those from geometric and poset theoretic perspectives, I moved on to something we now call dynamical algebraic combinatorics, which is something that Oliver and I have collaborated on in the past. And we're looking at dynamics on fun combinatorial objects, and especially situations that turn out to be very nice. So anyway, you'll see something that looks like this. This is a tableau. That'll show up in the talk as well. And then the third area of my research, which is newer and which is not an acronym, is just the word web. So I'll tell you about what webs are and what web bases are. And in fact, I really enjoyed working on this project. And in fact, we're still continuing to work on follow-up results. And one reason I like it so much is it brings together all of the things that I've studied and that I really enjoy in kind of a surprising way. Like the project I'm going to tell you about, I thought was more over on this side, but then my favorite objects, alternating sign matrices, ended up popping out. So first I should tell you what those objects are. And it doesn't matter too much for this talk, but they're defined with just like three simple conditions. One is that the entries have to be 0, 1, or -1. Also, each row and each column sums to 1, and the non-zero entries need to alternate in sign along a row or a column. So in fact, permutation matrices satisfy this definition, but as do a lot of other matrices. And so we're combinatorialists, so we like to count things. So if you were to ask your computer to tell you how many alternating sign matrices there are for a fixed size, well, it would do it up to about n = 7 unless you were clever. But anyway, so here's the counting sequence. And it turns out that there's a lovely counting formula that enumerates these objects as well. This was conjectured in 1983, but it took over 10 years to be able to actually prove it. And these proofs of the enumeration, especially one of them, brought to light a really interesting connection with physics. But I thought I would give you a little open problem that was supposed to be my thesis problem and is still open. So maybe don't work on it too hard, at least during the talk. But I hear you guys like generating functions. So if you want to just like put Q's on those factorials in the way that some of us saw in Josh Swanson's seminar talk yesterday. Anyway, if you Qify this formula, make it a generating function, what is it a generating function for? What statistic on alternating sign matrices gives you that generating function? Nobody knows. There's a lot of things that look like they work, but then as you go up to higher end, they don't. But anyway, I still think it's a really interesting problem. All right, but some things that you can do with alternating sign matrices is you can turn them into lots of other cool looking objects. So you can take an alternating sign matrix and turn it into a monotone triangle, something called the bumpless pipe dream, a height function, this thing that looks like a Pac-Man grid, which is a fully packed loop, or you can look at it poset theoretically as an order ideal in a tetrahedral poset. And one other thing you can do, which will be very relevant for this talk, is you can turn it into something that looks physicsy. So this is a configuration of the square ice model of statistical physics. And I've been told in talks before that ice doesn't actually freeze that way. But it turns out that you can find this model in real life in graphene. There was a Nature article in about 2015 that had stuff that looked like that. But anyway, we get tired of drawing H's and O's, and this is actually the only configuration of H's and O's I've ever drawn. We like to replace that with arrows on a grid. So this right here is a configuration of the six six-vertex model of statistical mechanics with domain wall boundary conditions, which just means on your square grid here, the top and bottom are pointing out, and the left and right are pointing in. And it's called the six-vertex model because the allowed configurations at any vertex are these 6 things. You notice there are 2 arrows in and 2 arrows out. And this is in fact a bijection with alternating sign matrices in that there's a given configuration for the 1 and for the -1. And you might say, hey, there are 4 different configurations for zeros. That doesn't look bijective to me. But it turns out it's okay. We know which ones of these zeros, like for any given 0, we know which one of these it should be, because basically you're just going to let the arrows propagate from the boundary through those zeros. Okay, so we have alternating sign matrices, and we have this 6-vertex model. Okay, so I want to think about how can we generalize this 6-vertex model and alternating sign matrices. So there are several ways that people have generalized these things. So one is by studying symmetry classes of alternating sign matrices, which you can think of as like, so this thing is symmetric across that vertical line. So you can really think of all the information as being stored here. So anyway, so these are like half alternating sign matrices that you can unfold to be a full alternating sign matrix. Or you could look at just partial alternating sign matrices. So my grad student Dylan Hoyer studied these and looked at various bijections recently. Some other things people have done is they've looked at the fully packed loops, those Pac-Man type grids on general domains, which is really sort of an instance of what I'm showing here. So this is like a hexagonal, a bunch of 4x4 partial alternating sign matrices chained together. And I ended up studying these things with my very first graduate combinatorics class of 5 students. And so we did a bunch of different bijective things on these ASMs. We turned them, well, first of all, we split them apart into a bunch of different matrices kind of chained together. And then we turned them into 6-vertex configurations as well. And you notice this domain wall boundary condition thing keeps going. Like we're being very particular with our boundary conditions of out, in, out, et cetera, so that it ends up having that same sort of flavor as the original domain wall boundary conditions. But the question is, given a 4 regular graph, how could we make a 6-vertex configuration on it? So here's the slide with the original 6-vertex model. And I told you about these boundary conditions, which we care about because we end up getting in bijection with alternating sign matrices this way. But like, it's very important that you're on a square, right? That you're going out on the bottom and the top, and you're going in on the left and the right. So if it wasn't a square, how would you know what to do with those boundary conditions? Well, we ended up changing this model a little bit just by flipping around all the vertical arrows. So now all of our boundary conditions are pointing in. And when I flipped around all the vertical arrows, it just kind of permuted all of these configurations. Those still have 2 going straight through in each direction. But it turned the 1 and the -1, instead of a 2 in, 2 out thing, it turned the 1s into sinks and the -1s into sources. And now we have a model that we can put on any 4 regular graph. So this is what we call a symmetrized 6-vertex configuration. It's a planar graph embedded in a disk. So we're imagining instead of being on a square, now we are on a circle, and all our exterior arrows are pointing in. And then each vertex has to be a source, a sink, or what we call a transmitting vertex, which is any of these kinds where things are going straight through in each direction. All right, so we're interested in studying this model, but not for any of the reasons that you might think given the start of this talk. Really, we stumbled upon this model while studying something else. So I'll ask you to watch carefully. I'll take this symmetrized 6-vertex configuration, and I'm going to turn it into an hourglass plabic graph. And that's the thing on our t-shirt. OK, I'll tell you more about this as well. But I'll go back and forth a little bit. You can kind of see what happens. So at spots where we had a transmitting vertex like this, what ended up getting put in here was a little twisted edge like that, which we will call an hourglass edge. And then, let's see, some other things. If you look at this vertex, this was a vertex that was a sink, and it just turned into a white vertex. And then similarly, I guess I don't have a black vertex that doesn't have an hourglass on it, but a similar thing would happen to the sources. OK, so we were studying these objects. And so So the question is, really, why were we studying these objects? And what does it have to do with this six-vertex model and the dynamical algebraic combinatorics? And really, what else does it have to do with the alternating sign matrices? Okay, so I'll tell you a little bit. Plabic graphs were already a thing. We added this adjective hourglass in front of it. And really, we used these objects to solve an algebraic problem. And that's kind of the game of algebraic combinatorics, is that we want to, instead of doing lots of complicated algebra, we want to just be able to draw pictures and say this picture represents some sort of polynomial that is a basis element for some complicated space. So that's what we're going to do, and I'm going to try to show you how. Okay, so first of all, let's start with the plabic graph. So notice this is very similar to the previous picture, except there aren't any of those little squiggly hourglasses. Okay, so a plabic graph is a planar bicolored graph embedded in a disk with all the boundary vertices of degree 1. And these plabic graphs were introduced by Postnikov, and they were really useful for a lot of things that are on this slide, like cluster algebras and scattering amplitudes. So people in algebraic combinatorics really like, many people in algebraic combinatorics really like plabic graphs because they help study all of these other complicated objects. Okay, so we kind of did we added something to this definition, and we'll say an hourglass plabic graph is a planar bicolored graph. It's really bipartite now, but in the other definition it didn't have to be. And then all the internal vertices are of degree r. So this is a 4 hourglass plabic graph because these vertices in the middle are of degree 4. And notice that we're counting these hourglass edges as like a degree 2 edge because there's 2 little edges coming in there. So if you look at all the internal vertices, they're all of degree 4. And pay no attention to the colorful paths on there for now. I'll tell you what those mean in a moment, so pretend that those aren't there. But yeah, whenever we have a multiple edge, we're going to draw it as this kind of twisted hourglass. And it also will matter what it looks like around the boundary. Here we have 16 boundary elements. They're all black dots. So we're going to say this is boundary type 1, 1, 1, 1, 1 with a whole bunch, well, with 16 ones. So I'll show you a couple more examples of our hourglass plabic graphs. So here's one. This one kind of looks interesting. So notice there are some hourglass shapes on the boundary, and that's okay. So this is one of boundary type, well, every time there's a black vertex, we're going to just record how many edges are in that hourglass. So the first one is a 2. But this is a white vertex, and there's only one thing coming out of it. So this is a -1, or I'll call it as a 1 bar. And then here's a +3, +1, -2, etc. So we can write down what the type is of that around the boundary. And then here's one more, which will show up near the end of the talk. So you can see these like onion hourglassy things can get kind of big. But there's one, this is a 9 hourglass plabic graph because every vertex has degree 9 in the interior. Okay, so these are very pretty pictures, but more than being pretty pictures, the reason that we were interested in these is we were able to figure out that these pictures represent polynomials that give us a basis for some complicated algebraic space, the invariant space of UQSL4 for that wedge product associated to the type around the boundary. Okay, but I don't want to say all that because it's a mouthful, so let's just call this a web basis for SL4. And I'll tell you what it has to do with the special linear group shortly. Okay, so these are our graphs. These are 4 hourglass plabic graphs, and they have all these adjectives in front of them. So we wanted to be able to say, each of these graphs represents some sort of element of some algebraic space, and we wanted to know which elements give us a basis for that space. So we had to figure out what are all the properties of such a graph that tell us it's really a basis element. And so I'll tell you what all of these things mean shortly: contracted, fully reduced, top. But those are all the adjectives that go along with the kind of hourglass plabic graphs we want. Or we can do adjectives in this 6-vertex configuration. So there's actually a nice bijection between these, which is basically what I just showed you about squishing the hourglasses. So these are 2 different ways of looking at the same polynomial invariant for some algebraic space. Okay? Now I have to do a short sidebar on what are webs. I guess, did I use the word web over here? Oh, yes. So the punchline of this theorem is that we have a rotation-invariant web basis for SL4. Okay, so rotation invariant is easy. We want the property that if you take this graph and you rotate it, you also get a basis element. Okay, so that's what rotation invariant means. And it means, we have a description of exactly which graphs these are also, but when you rotate them, you still get a basis element. And then the question is, what is a web basis? So web is a word that has appeared before our work. A lot of people have studied things called webs. And so here's what it is, the definition that we used in our paper. And I'll try to show you how to calculate a polynomial from one of these graphs. Okay, so a web is a planar, properly bicolored graph embedded in a disk with boundary vertices of degree 1 and interior edges summing to a certain number r. So here, all of these interior edges are just of degree 1. Oh, and then there's like some tagging convention, but don't worry about that. Anyway, so the idea here is web bases are things that have been studied. They're diagrammatic bases for invariant spaces, so that each invariant is encoded by a web, and you can actually use these webs to calculate, to do algebraic operations. So if you smash two webs together, it's like multiplying or adding polynomials or whatever. Okay, so what polynomial is associated to each web? I'm going to be very sloppy, but basically if you have something that looks like this, it's really a determinant. So you're imagining that each of your exterior vertices is some sort of vector, if it's a black vertex, or a covector if it's a white vertex. And then if you are putting them all together, you're getting a determinant. Here's something slightly more complicated. So notice here's some vectors for the black vertices and some covectors for the white vertices. And you start multiplying things together in the sense of taking minors of the matrices when you smash them together. And what you're going to end up getting as the polynomial invariant in the end is this big vector times this big vector. So you just start taking your vectors and covectors and taking minors to make new vectors or matrices and multiplying things together, and you end up with some giant polynomial. And I would much rather write down this picture than that whole giant polynomial that I didn't even write down because it was too much. Okay, so webs have been studied by a lot of different people, and many of the definitions are just a little bit different. You have to be careful as you read these papers, but the idea in all of them is that we're trying to represent algebraic basis elements, or algebraic spaces, elements of an algebraic space with a picture. Okay, and the big question, so webs were known by these people before, but the big question is there, can we find a basis, a nice basis, a basis that has the properties that we want, namely this rotation invariance and some other cool stuff. Okay, so here's our main theorem again. Here are the two main pictures, and here in the middle is one of our favorite objects in algebraic combinatorics, a tableau. Okay, so really, I've been telling you the whole story backwards. I started with symmetrized six-vertex configurations. Then I told you a little bit about web bases and the algebraic problem we're trying to solve. And now I'm finally adding in the dynamics, which is represented by this tableau. And that's really where several of us started the project. In fact, Oliver and I were trying to draw diagrams that exhibited good dynamics years ago. And now we finally have had the tools to put this together so that we could have this nice rotation property that exhibits some good combinatorics. So I need to tell you a little bit about Tableau, and then we'll come back to see what combinatorial dynamical property the Tableau and the webs, what connects them. Okay, so here's a Tableau. So this is a standard Young Tableau. It's just a filling of a partition shape with numbers so that our rows and columns, are increasing, and each number is used once. So these are nice objects that we can count. And it turns out that there's a nice hook content formula that says, okay, the number of ways to write down one of these standard Young Tableau is going to be n factorial. So in this case, it would be 11 factorial, divided by some numbers that are called hook lengths of each box. So it's a really nice, easy formula, the kind of formula that we love for counting objects. For this project, we cared a lot about those standard Young Tableau, but we also needed to kind of generalize the stuff people like about Tableau to something more complicated. So this is a fluctuating tableau. And maybe I'll show you something about a standard Young Tableau, and then I'll show you how that weird fluctuating tableau I just showed you relates. So a standard Young tableau, you can think of this as like growing a partition shape where the numbers tell you how, like when to add the boxes, right? So you're just like growing the shape. Here, this fluctuating tableau is telling us how to grow the shape or maybe shrink the shape. So the ones here, so we're allowing multiple of the same number now, only in a column though. And so these ones say, let's grow our shape here, but here is our base, like here's 0. This 2 bar says we want to actually subtract a box in that column, but now the 3 says we're going to add in this one, and we're going to add in this one, and we're going to add this one back in, so we're going to get rid of that negative box. So anyway, the pluses and the minuses tell you if you're adding boxes or taking them away. And there's been lots of different kinds of tableau that people have studied, and this class of tableau kind of includes a lot of those special tableau people have studied. Okay, so I want to tell you about some dynamics on tableau, and I'll do this in the standard case because the fluctuating case is kind of confusing. Okay, but here is a fun operation you can do on tableau, and it has some fun properties that I'll tell you about. So promotion says, all right, let's erase the 1. So there's always going to be a 1 in the upper left-hand corner by our rules for standard tableau. And now we want to ask ourselves, okay, it's kind of like one of those little puzzles. Have you ever, like with the missing corner, and you like move things around and you try to make the picture? I'm terrible at those, but I like this. Promotion is fun. Here I'm going to ask myself, which of these do I want to slide into this box? What do you think, based on no information at all about what you're going for? But which one do you want to slide? 2. Yeah, I want to slide the 2 too. It would make me feel really bad if there was a 3 before the 2. Like that would be bad. So let's slide the 2 over. Okay? And now we have a box, and what number do you want to fill in there? 4. Yeah, the 4 sounds good, because then the 4 would be less than the 5. So we're going to just keep doing that and look to the box to the right and below to ask ourselves which one we want to slide in until we end up with an empty box on the outer corner. Okay, and now, well, what should we do with this? We could just get rid of it and have a smaller shape, but I really like rectangles, so let's not do that. So let's fill this with the next biggest number, and then what could we do to turn this into the kind of object we started with? Subtract 1. Let's just subtract 1 from everything, and then we have the numbers 1 through 16 again. But as it turns out, they're in a different, they're in different boxes than what we started with. So this is an outline of everything we just did. So here's where we started, and here's where we ended. And notice, for instance, this is a 2 here, and this is a 3. These are different tableau. Okay? Okay, this is my fluctuating tableau slide, which I'm not going to explain, but you can do the same sort of thing on a fluctuating tableau. It's just kind of annoying. Notice you have like 2 empty boxes, but the empty things end up filling boxes with other guys. I said I wasn't going to explain it, and there's a reason why. All right, so, but both of these shapes that I've shown you are rectangles. Yeah, this one is kind of obviously a rectangle. This one, if you do all the, anyway, it's shaded as a rectangle. Here's the rectangle. If you do all the adding and subtracting of the boxes, you end up with a rectangle. Okay, so that's what we mean by a rectangle here. So notice like the 3, in step 3 we added this box, but in step 7 it's gone, right? So all of these have an even number of pluses and minuses, but here we have 2 pluses and a minus, so that box is still there. So anyway, if you have a rectangle, it is true, it is known that if you do promotion, a certain number of times, you're guaranteed to get back the same tableau. So that certain number of times for this guy is 16, because it's a 4x4 box. Okay, so if you do that whole promotion process I showed you, we did it once, but if you keep doing that over and over and over again until you've done it 16 times, you are guaranteed to be back to the one that you started with. And the big question is, like, why? We were just like sliding a bunch of numbers around in boxes. It's not at all obvious why it would take 16 times to get back. Okay, and then over here, this is something that we proved recently because we had to like make up this new set of tableau, but it's basically the same kind of proof as this one. Here you would have to do promotion 7 times because the numbers go up to 7 to be guaranteed to get back to the tableau that you started with. Okay, so that's what these 2 theorems say, is you do promotion that number of times and you will get back to the tableau you started with. And now this is not at all true if you don't have a rectangle. So even if you just make, just like a, well, okay, maybe not that, I don't know. Anyway, like some other shape that's not a rectangle, it could take a really, really long time to get back to the tableau that you started with. Okay, so rectangles are just like wildly well-behaved, and the question is, what's so special about rectangles? So I'll give you a few answers to that. One is something that we were looking at in the course of this work, is that rectangles have promotion permutations. And I will not use this definition up here to tell you about it, but rather, so there are going to be these three permutations, and I'll slide over here to tell you what's going to happen. So this is promotion permutation 1. The first entry in here is 4. And if we go over here to look at what happened in that promotion process, we see that there is a unique number that slides up from row 2 to row 1. And that unique number here is 4. And that's why this number is a 4. Okay? And then if we kept doing promotion over and over again, if we started here and we asked what unique number will go from the second row to the first row, which one would it be? If we erase the 1 and start doing the process, what will move from the second row to the first row? The 2, yeah. And as it turns out, well, that's not a 2, but it's a 2 plus 1. So you have to add 1 for each time you do promotion. So anyway, you could construct this whole promotion permutation by doing promotion 16 times and asking yourself what moved from row 2 to row 1, and then just adding I for if you're on the ith step. Okay, so this permutation is something that you can construct. Now, why is it a permutation? That's something you have to prove. There's like lots of nice properties about these things, but as it turns out, it is a nice permutation. And as it turns out, there's a way to basically extract all the numbers for each spot in your tableau just from looking at these permutations. And then there's these other two permutations. This is promotion permutation 2 and promotion permutation 3. And those are constructed just by asking what moves from row 2 to row 1. And what moves from row, no, sorry, I drew the right thing. What moves from row 3 to row 2, and what moves from row 4 to row 3. So I think I even drew the arrows in the right spot. The 14 ended up moving up, right? So anyway, so you can construct all these permutations, and you can even draw them. Okay, so here I've drawn promotion permutation 1, promotion permutation 2, and promotion permutation 3, and you can even see here that there's something special about these permutations. So if you look at this one and this one, they kind of look the same, right? What's the difference?
Inverse.
Yeah, they're inverses of each other, right? The arrows are going in the opposite direction in each of these. And here I haven't drawn arrows because it turns out that promotion permutation 2 is an involution. So it is its own inverse. Okay, and these are things that are summarized right here in this theorem. We proved all these things about these promotion permutations. They exist. They satisfy this nice inverse property. And, oh yeah, the thing I didn't tell you about, but is kind of true by construction, they rotate. So if we were to do promotion once to that new tableau, look at its promotion permutations, then they will be the rotation of these things. So we almost have a model here that would tell us something about why when you do promotion, it takes 16 steps to get back to where you started, because we have these things on 16 numbers around your circle that rotate when you do promotion. So this is sort of like an intermediary step between this and the hourglass plabic graph stuff, and I'll show you how to get there. So here, we like this model, but we don't actually know how to characterize these permutations. So it doesn't work as a real explanation for this phenomenon of getting back in a certain number of steps. Okay, oh, and we can do this. It still works in the fluctuating case. So here's promotion permutation 1, 2, and 3 for that fluctuating tableau. Okay, so now I want to tell you a little bit more about the algebraic problem that we're trying to solve and what's been done before our work. And then you'll see kind of how it all fits together, the dynamics and the web stuff. Okay, so let's go back to the algebra. And suppose you have a whole bunch of variables. We can ask which polynomials in those variables are invariant under SLR. Okay? And you can think of SLR as a whole bunch of R by R determinants. It's spanned by products of those. So here is an SL2 example. So here's a polynomial that's going to be invariant under the action of SL2. You can imagine just like multiplying this big old polynomial, or like doing a change of variables where like you multiply all your variables by like A, B, C, D, that little matrix of determinant 1. Anyway, so it's like some polynomials. And here's a standard answer. The standard answer says that if you want to, for example, look at SL2, all you need to do is write down all the standard Young tableau, and then write down some monomials that correspond to those tableau, and that'll give you a basis for this space. So here's a tableau, and so for example, 1, 4 gives us this little matrix minor. Notice the second coordinate for each of those x's are 1 and 4. So each of these columns gives us a matrix, and so we say this polynomial is a basis element in the standard monomial basis for SL2. But it's not a rotation-invariant basis, which if it were a rotation-invariant basis, we would be able to cycle all of the numbers by 1, right? We could turn this into a 2, this into a 3, this into a 4, but this one would end up being a 1 at the end, and that thing is not a standard Young tableau, right? Because the numbers aren't in order. So it's not rotation invariant. So this, in some sense, isn't quite what you want to solve this algebraic problem. But there's a different basis that people know called the temporally lead basis. And there's a nice combinatorial bijection that goes along with it. So you can take any standard Young tableau and turn it into something called a non-crossing matching. And then this, so I'll tell you in a moment about that bijection, but it's a nice, easy bijection. And then with this matching, notice 1 is matched to 10, so that's the matrix minor that you write down with the 1. The second coordinate is 1s and 10s, not 1s and 4s. Okay? Oh, does anybody know how many of these things there are? What are they counted by? These are the Catalan numbers, yes. And then there's also a nice easy bijection between these things just by saying, okay, look at the stuff in the top row here. Those guys should be the smallest number in their pair. So notice each of 1, 2, 3, 4, and 7 is the smallest thing, and then you just connect everything up so that they're non-crossing. Oh, and one other thing we should notice is that you can think of these guys as SL2 webs, right? Each of these little arcs is just an arc connecting two boundary vertices connecting to a middle guy. And so that's what I already described with webs to say, like, this should represent a 2 by 2 determinant. Oh yeah, this one. So the question is there something that you can do to Tableau to turn it into something that rotates? Because notice this is a rotation invariant basis. If I rotate one of these non-crossing matchings, I get back a non-crossing matching. Well, so here's some combinatorics that can be our guide. So we already talked about this bijection between Tableau and these non-crossing matchings. And we already talked about promotion. And as it turns out, when you do promotion over here on these 2-row rectangular Tableau, it just rotates this non-crossing matching. So that is a super nice explanation for why it takes, why you know that after 10 steps of promotion, you get back to where you started. You get back to the Tableau you started with, because over here, you know that after 10 steps of rotating, you get back to where you started. Okay, so this is like a visual explanation for a really lovely combinatorial fact about this action, or this action over here. It really is a rotation in disguise. Okay, so we'd really like this story to generalize because we know that promotion on rectangles is nice. It looks like it should be a rotation. Okay, and in fact it does generalize if you have 3-row rectangles. Both the algebraic problem, so the rotation invariant basis for SL3, and this combinatorial bijection, they both work. So Kuperberg, and in joint work with Kovanov, defined some things he called SL3 webs, which look a lot like this. So SL3 webs, we already defined what those are, but he found which ones should be the basis elements. And namely, Kuperberg said, if your web is non-elliptic, meaning it has no cycles of length less than 6. So in particular, what's not allowed on the inside of this web is a length 4 cycle. You can't have a square. You also can't have a length 5 cycle, but that's just because it's bipartite. Okay, so you can't have a square, no squares. No squares allowed. Okay. All right, so this solves the algebraic problem for SL3. which corresponds to 3-row rectangles. And then Peterson, Pulaski, and Rhodes showed that promotion, when you do promotion on the 3-row standard Young tableau, you end up rotating the corresponding web. So there is a really nice bijection between these tableau and these SL3 non-elliptic webs. And promotion corresponds to rotation, and it completely matches up with that, with the SL2 story that I showed you with the non-crossing matchings. Okay, so at this point, a lot of us knew this story, and I remember one time being at a workshop with Oliver, and we were skipping a talk, and we were drawing pictures. We were trying to figure out, is there a way that if we have these 4-row webs, what kind of picture should we draw? Well, this guy is trivalent in the middle, right? It's an SL3 web, so we decided that we thought we should have pictures of things that were bipartite that had degree 4 in the middle, and we wanted those to rotate with promotion. So this was really at the heart of what we wanted to do. We knew that it also solved this algebraic problem, but this is the combinatorial heart of this project, is we wanted to find what rotates when you do promotion. But we drew some pictures, and it just seemed like the stuff that we were guessing almost worked, right? Sometimes it worked, but there were these cases in which it didn't work, and then we didn't know what to do. And then also, I guess about 10 years later, our friend Becky Petrius looked at, so this was just for the standard Young tableau that we got rotation and promotion. She defined a promotion on something that looks very similar to our fluctuating tableau. It's just like one level of generality less, and she showed that promotion over here corresponds to rotation of these SL3 webs, now with boundary vertices that could be black or white. Okay, so these were also things that solved the algebraic problem in the work of Cooperberg, and they also have this nice promotion corresponds to rotation property. Okay, so we were just over here trying to solve this for 4 rows, but the promotion and rotation thing actually held more generally for 3-row tableau. So here, finally, is a new tool that helped us figure out this problem for 4 rows. And this is the observation of Hopkins and Ruby in recent work that plabic graphs are webs, and webs are plabic. Okay, one way or the other, one of them is the other kind of thing, right? So these definitions I've been giving you of like web and plabic graph, they all sounded very similar, right? So some of them, plabic graphs technically don't have to be bipartite. Webs have this constant degree of internal vertices. But anyway, in principle, these are the same things. So in the spaces where those intersect, we can use tools from one realm to help us out in another realm. And so this observation said, let's use this tool from plabic graph world called the trip permutation, and let's pull it over to web world and see if that helps us over there. So what they said is there's something called a trip permutation. So take this, interpret it as a plabic graph, and here you're going to be a crazy driver. You're going to follow some rules of the road. So you're going to start at some vertex and decide you're going to turn left at each white vertex and right at each black vertex. So I'm going to start here at 4 and go left, right, left, and I ended up at 9. And the 4th element of that permutation is 9. And what Hopkins and Ruby found is that this trip permutation that I just showed you actually matches up with this promotion permutation I showed you on the tableau side. Okay, so they were looking at what moves from row 2 to row 1 in each iteration of promotion, and that turns out to match up exactly with this trip permutation. So this is the trip equals prom property for 3-row tableau. So this was the thing that we could use as a guide. Now that we know we want to draw pictures such that promotion rotates, but also such that we have these trip permutations that are supposed to match up exactly with those promotion permutations. So here, again, is our main theorem. And I still haven't told you what contracted, fully reduced, or top mean, but we'll get to that. I have told you about these other bullet points, though, in the other cases. So promotion should correspond to rotation, and the trip permutations should equal the promotion permutations. And in fact, they do. So these trip permutations I showed you, I'll show you that in a second when I have the permutations written out. But basically, that's what these colored lines are these different ways of driving around on your graph with these trip permutations. Okay, but before I finish filling in all of the parts of the theorem, I want to tell you just a couple words about the proof. So this is supposed to be a bijection. It's a bijection between tableau and, in fact, equivalence classes of graphs in some sense. So we have some rules that will help us grow a graph from a tableau. They are very complicated, so I don't advise actually using them unless you have a computer. But anyway, we have a way to grow the graph from the tableau. And then also we have a way to take a graph, now that we know which graphs we want, and label it a certain way so that we can recover the tableau. So I'll tell you what these things mean, sort of one at a time. And there's nothing new up above. This is just another picture. So the fluctuating tableau will correspond to this plabic graph hourglass plabic graph that I've already shown you. So, okay, so now I'm going to tell you about some of these adjectives. How do we know which graphs to pick? So we want them to be contracted, fully reduced, and something called top. Okay, so contracted means you don't want to put, in our case, too many double hourglasses in a row, because that would be kind of silly. If you just had an hourglass and then another hourglass, well, you could have just like squished that whole thing and turned it into a vertex. So don't have too many hourglasses in a row. And then we have some moves. So this picture you should kind of look at separated into two parts, which maybe I should just draw a line there. Okay, so here are all the moves. So we're going to kind of consider a graph to be equivalent under these different moves. So the ones on the right are called square moves. And you can kind of see a pattern in all those different possibilities. Where there is an hourglass coming out from a square, it gets squished, and where there isn't, it gets unsquished, and the coloring around the square gets reversed. Oops. All right, so those square moves are very nice. They're well studied in the web literature and actually on the plabic graph side as well. But the web people know that when you do these moves, you don't actually change the polynomial that you correspond to the web. So those moves in some sense don't matter. And then our other adjective, top, means, so these moves over here, these things we call benzene moves, because they look like benzene rings from chemistry. So those moves do matter. They do change the polynomial. But you can do as many. So if you imagine you have a whole grid of a whole bunch of hexagons, you can just like go around and start doing a bunch of moves to all of those different hexagons until you get to your preferred of the two configurations. So let's just say we prefer that configuration where the white is always clockwise of the black in an hourglass. Okay, so you can get to a preferred configuration there, so that will give you your polynomial that we want to be a rotation-invariant basis element. Now, the other adjective on what kinds of graphs do we want is fully reduced. So fully reduced in this R equals 4 case means no graph in the move equivalence class has a 4 cycle containing an hourglass. So here are all the ways that that can go wrong. So if you have a square, it needs to not have anything weird going on. It just needs to have single edges around it. And we think that we will be able to look at this in general. In general, what's going to be true is that the sum of the multiplicities around a square must be at most r, which explains why for the 3-row tableau, for the SL3 case, you couldn't have a square, right? Because 1 plus 1 plus 1 plus 1 is 4, which is bigger than 3. Okay, so this works for the known cases of web bases as well in lower R. All right, here's where I was going to tell you about the separation labeling. So if I give you one of these webs, one of these hourglass plabic graphs, how do you get the tableau? Well, what you're going to do is you're going to look at trip permutation. So I told you about taking a left at a white and a right at a black. So here we take a left and a right and a left. And so 9 goes to 13 in trip 1. So here we are, 9 goes to 13. But there are other choices. Now that we have degree 4 at the vertices, we just take a left. We could also go straight, or we could take a right. So we're going to try all of those things and make 3 different trip permutations for those. So this yellow one is the one where I choose to go straight through every intersection. No turns for me, except some of them look weird because of those hourglasses. Okay, but for trip 2, we started out at 9, we got to 2. So that was right here. And then similarly for trip 3, now we take a right at white and a left at black. So anyway, for each for each boundary vertex, we can do all of those different trips and then write down these 3 different trip permutations. And so in that sense, those 3 different trip permutations match those 3 promotion permutations. And the way that we can do this is, what we end up looking at is, so here's the base face. That's the spot between the 1 and the 16. And here we're going to look at this edge and ask ourselves, let's label this edge. It turns out we're going to be able to label all the boundary edges with numbers that will help us recover this tableau. Okay, so the way that we look at this, or label this edge, is we look at this starred region, and we ask ourselves, how many of these trip permutations separate me from the other starred region? Okay, so how many of those colorful graphs separate the 2 stars? Or colorful paths, the 3 colors on there? There's the purple, the yellow, and the blue. What? 2. Yeah, 2 of them. The yellow and the blue separate, and the purple one doesn't, right? So 2 of those separate. So I'm actually going to label this with a 3. I'm always just going to add 1 to however many of them separate. And it turns out that 9 is in the 3rd row over here. Okay, so we do that for each of these boundary labels, and that ends up telling us where the numbers 1 through 16 go in our tableau. And if we do this and the neat thing is, if we do this labeling of the edges throughout the whole graph, it's going to be a proper labeling. So each vertex is going to have an edge near it, or adjacent to it, that is labeled 1, 2, 3, or 4. Okay, so trip equals prom, and that's kind of how the separation labeling works. Here's our main theorem, 6-vertex style. So we call these things well-oriented, top, symmetrized 6-vertex configurations. So these are the adjectives I showed you before. They have a natural translation to the 6-vertex model. And it turns out that this model for our basis elements was very helpful in proving a lot of the things that we had to prove to show that this was our rotation-invariant basis. Okay, so here's that same picture, only 6-vertex style. So here's what the different moves look like. So all of those square moves on the right now look like these 6-vertex versions. And then here's something that looks like pictures you see associated to the Yang-Baxter equation in physics, or Reidemeister moves in knot theory. So we have that move as well. So these are all moves that you can apply to our 6-vertex configurations to get things that are in the same equivalence class. Okay, so in the last couple minutes, I want to circle back to alternating sign matrices and tell you how these show up. So here are my favorite objects. Here are the 3x3 version of my favorite objects. There's 7 of them. There they are. And it turns out that all of these correspond to this very nice tableau. Just the tableau where you put the numbers in there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can do our bijection and get all of these guys. And here they all are in their 6-vertex version and kind of a post set associated with them. But we were able to say, okay, we know that all of the things that correspond to this tableau in our equivalence class are actually these alternating sign matrices. And at that moment in our group meetings, when I figured out that, wait a minute, I've seen these things before. These really are my favorite objects showing up in a project that I thought had nothing to do with them, like made me exceedingly happy, one of my favorite moments in all of my mathematical career. But it was even better than that, because not only were my first favorite objects in there, we also found plane partitions as equivalence classes in our set of webs. So plane partitions are stacks of cubes in a corner, kind of like that, and I drew the web on top of it that corresponds exactly to this plane partition. So here the tableau is a little weird. It's one of these fluctuating tableaus, or tableau. But all the plane partitions over here, all the ways of stacking cubes in this box correspond in this bijection to this tableau. Yeah, okay, and then back on plane partitions, which we don't really have time to look at, but the idea here is that there are symmetry classes of plane partitions, and they're very nice. They have nice enumerations. It turns out that particularly pretty ones should be in bijection with alternating sign matrices, and nobody knows how to do that, which is a very intriguing open problem. But here, we're going to explore this symmetry class from the perspective of webs. So if you have this very symmetric thing right here, you only need a little bit of it. So we're going to just draw a web on top of this fundamental domain and ask which tableau does that web correspond to? And with my grad student, Ashley Adams, we wrote down the answer to which tableau correspond to this special class of plane partitions, which are some of my favorite objects as well. All right, and then lastly, in another paper with this same set of collaborators here, we looked at tableau of any length as long as there's only 2 columns, and we know how to write those down as webs as well, and that solves a rotation-invariant web basis problem for a slightly different space. Okay, so the question that you would ask if I had stopped and asked for questions is, what now? We can do 4 rows. We can do 2 columns. What about 5 rows? What about beyond? So we have some guiding combinatorics in the search for this. That promotion on your tableau should correspond to rotation of your graphs, that your trip permutations should equal your promotion permutations. And in fact, we are all gathered here in Waterloo this week to try to work on SL5 and maybe beyond. Okay, but for SL5, we do have an analog of the benzene move. Here is a picture of the square move. In fact, web people know that the square move works in general for whatever, so these m's are representing multiplicities of these edges, like how big are those hourglasses supposed to be. So the square move should work. We kind of know how the benzene move works. We were just upstairs looking at more complicated moves. So we'll see. We're very hopeful that we'll be able to do SL5, and who knows beyond that. But it is a really intriguing dynamical mystery about why promotion for any size rectangle should have this nice order that matches with the rotation, and we're on the hunt for that. So thank you very much. Questions? Mm-hmm.
So when you're moving to like cases for like SL5 and beyond, you're talking about like analogous moves, I guess. Like, what are the more complicated moves that like you would be thinking of, and like I guess kind of like how do those play a part?
Yeah, what do the more complicated moves look like? Well, they end up being moves involving some hexagon, just like our benzene move. Well, that's a few too many pages back. Our benzene move was basically, for SL4, was basically a hexagon, right, where you had an hourglass at every other spot. And it would switch with the one, like basically move the hourglasses around, right? So we have analogs of that, except now our graphs are 5-valent. So we have like, 3 hourglass and 1 and 3 and 1, and that cycles around. But then there are some other more complicated ones that really we only found because Josh and Stefan wrote some really amazing code that can produce these graphs and help us explore this space of graphs to see which ones have the same trip permutations is really what we were looking at. So anytime there were 2 graphs that had the same trip permutations, that told us, the trip permutations completely describe the tableau. So that told us those 2 graphs should be equivalent. So we've been exploring that. And so, yeah, we have some other moves that end up looking like a hexagon and a square, kind of smashing through each other. So, they are a little bit weird. But we think we have a handle on them. So that's a big task for us this week. Yep, well, yeah?
So somewhere in the middle of your talk, so you were showing how to assign integers to the vertices on the outside. Mm-hmm. Could you go back to that slide?
Yeah. Let's see. I'll try to do it.
To determine the type of that web?
Yeah. Yeah, here? Yeah.
No, it was a longer...
Long time ago? Okay.
Yeah. When you were saying that the webs have a certain
Oh,
type.
yeah, the types of the webs. Sure, yeah, that was a long time ago. I agree. Let's see. Oh, like this one? This is the weirdest one.
Yeah, so do you have local moves that allow you to swap labels in adjacent vertices?
Oh, to help us change between different types here?
Yeah.
No, we've mostly been looking at moves within like we fix the type, and then we're looking at moves on the graphs inside. Josh is wiggling.
The growth rules.
Oh, the growth rules.
So you need some kind of ascent action. We do know how to do the ascent action. By crossing over and then have some
Yeah,
other
yeah.
relations.
Oh, okay.
Yeah, we have skein relations and stuff that I should have shown, but yeah, we have ways to take diagrams that are crossing and stuff and uncross them to get to these things. So
Okay, well, maybe I can ask you about that later.
yeah, sounds good. Yep, Karen.
When I'm in positroid land, maybe I don't find plabic graphs my favorite ones because of these moves, and some of the other bijective things sort of aren't up to moves, and so I feel like maybe I like those better. Is there any hope here of doing something simpler, of having some nice combinatorial object that does it on the nose without needing to be up to moves?
Well, that's sort of what I think that's where people have been stuck for a long time, and why this has been open for like 30 years is we've been looking for that. But like if we want these properties about like rotation and promotion matching up, you know, that's where we were getting stuck as we were drawing. We were like, oh, well, this one, we drew a graph that has rotation order 4, but we know promotion should be of order 2. So really, the graph and the thing that you get in rotating 2 steps should be the same. And so yeah, so I know that does bother people a little bit that you have these moves, but in some sense, at least in this SL4 case, it isn't so bad because the square moves don't change the polynomial. And these benzene moves, we can figure out which one that we want to take as our representative. So. And we have work in progress on a geometric interpretation of the whole move class of stuff to make it like a bigger two-dimensional thing. So yeah.
Well, if there's no more questions, let's thank Jessica again.